everyone, thank you so much for clicking onto the video. Today's learning objectives are to firstly look at the weak acidity of phenols shown by the neutralization reaction with sodium hydroxide, but absence of reaction with carbonates. Then we're going to look at the electrophilic substitution reactions of phenol with bromine to form 2,4,6-tribromophenol and with dilute nitric acid to form a mixture of 2-nitrophenol and 4-nitrophenol. We're then going to look at the relative ease of electrophilic substitution of phenol compared with benzene in terms of electron pair donation to the pi system from an oxygen p orbital in phenol. Then we're going to look at the 2,4 directing effect of electron donating groups and the 3 directing effect of electron withdrawing groups in electrophilic substitution of aromatic compounds. And finally, we're going to look at the prediction of substitution products of aromatic compounds by directing effects and the importance to organic systems. So now we're going to talk a bit about phenols. In a phenol, the OH group is directly attached to the benzene ring, and the lone pair of electrons on the oxygen is delocalized with the electron charge cloud of the arene ring. So we've got that the OH group is directly attached to a carbon of the benzene ring, and also that the lone pair of electrons on this oxygen of the OH is delocalized with the electron charge cloud of the arene ring, so with all the delocalized electrons in the benzene ring. The delocalized bonding changes the reactivity of the OH group and the arene ring. And so we have that phenols are very weakly acidic, and they're actually weaker acids than carboxylic acids. Both phenols and carboxylic acids will react with sodium metal and also sodium hydroxide, because we know that a metal plus an acid would form a salt and hydrogen, and an acid and an alkali would form a salt and water in a neutralization reaction. Only carboxylic acids will react with sodium carbonate, however, as a phenol is not strong enough. We know that when we add acid with sodium carbonate, we form a salt, carbon dioxide, and water. But this doesn't happen when we use phenols. So an example of an acid-base reaction with a phenol is with sodium hydroxide. So we have a phenol, which is benzene attached to an OH. So we have benzene here, and we've got an OH attached. So this is our phenol. And then if we add it with sodium hydroxide, what we form is the salt and then water. So just like any other neutralization reaction. So we form the salt of O minus Na plus, and then the hydrogen, the H plus that we've just removed from the phenol, then reacts with the OH of the sodium hydroxide, so we get water. And the salt is called sodium phenoxide. So this sodium phenoxide compound formed is more soluble than the original phenol, and so overall what we get is that solid phenol will dissolve on addition of sodium hydroxide solution. So now we're going to look at the reaction of phenols with bromine water. So in phenol, the lone pair of electrons on the oxygen is partially delocalized into the ring, and so this increases the electron density of the delocalized electrons in the ring, and so we can polarize the bromine more. Because for benzene, for example, we originally have this hexagonal shape, and then we have this ring where we have all of these delocalized electrons. But in phenol, what we have is that we have an OH group here, and the lone pair of electrons on this oxygen actually are partially delocalized into the ring. And so basically we're adding more delocalized electrons into this ring. So that's why we increase the electron density. Phenols do not need a halogen carrier catalyst like benzene to react with a halogen. And this is because of the increased electron density. And phenols undergo multiple substitutions, whereas benzene will only add one bromine. So the reagent we use is bromine water, and we use room temperature. So the reaction we have is that we have phenol. So we have benzene, and then we have an OH. So this is our phenol. And then we react it with 3 bromines, so because it can undergo multiple substitutions. And then what we can form is, again, we have the benzene and the OH, but this time we have some bromines substituted. So we have one here, and also here. So what we formed is 2,4,6 tribromophenol. So we have 2,4,6 tribromophenol, and we also form HBr, and 3 of them, because what we've done is substituted the hydrogens which were attached to these carbons for bromines, and those have come out as H pluses and then reacted with the other bromine atom of all of the bromine molecules. And so that's how we get the 3 hydrogen bromides. And the product in this reaction is actually a white solid. So now we're going to talk about the reactions of phenols with nitric acid. So phenols react readily with dilute nitric acid at room temperature. And a mixture of 2-nitrophenol and 4-nitrophenol is formed. In comparison with benzene, phenol does not need concentrated nitric acid or the concentrated sulfuric acid catalyst that we have when we need to react benzene with the nitric acid. And this is because phenol has increased reactivity due to the lone pair of electrons from the oxygen p orbital of the OH group, which is attached to the benzene ring, being donated into the pi system of phenol, so into the delocalized system. And this increases the electron density of the benzene ring in phenol, and so attracts electrophiles more strongly. So the electrophile we're using here is the NO2+, which we saw also for the reaction of concentrated nitric acid and benzene with the concentrated sulfuric acid catalyst. But this time, because the phenol has a higher electron density, it attracts the electrophiles more, and so that's why we only need dilute nitric acid. So the reaction we have is that we have a phenol. So we have benzene and then OH. And then we add some nitric acid. So this is dilute. And we can form 2 products. So the first product we can form is this 2-nitrophenol. So it would be a benzene ring. And then you'd have an OH at the top, and then here you would have an NO2, and then you'd have water, because we've substituted out a H+, and the H+ has reacted with the rest of the nitric acid that we didn't use to form water. And the other product that we get is 4-nitrophenol. So we have benzene again, and again the OH. And now instead of the nitro substituent being on the 2nd carbon, it's now on the 4th carbon. So it's here. And again we form the water. And so this is 2-nitrophenol. So when we name this, we assume that the OH is on the 1st carbon, so because it's a phenol. And then the nitro group is on the 2nd carbon if this is the 1st carbon. And so that's why we name it 2-nitrophenol. So it's relative to the OH. And then this is 4-nitrophenol. So again, the OH group gets number 1, and then we go 1, 2, 3, and we also started off with this phenol. So this is an electrophilic substitution reaction. And that's because the attacking group is an electrophile, it's the NO2+ ion, and we're substituting that for a hydrogen. Now we're going to talk about the effect of side groups on substitution. So there are many different groups that can be attached to a benzene ring, and different groups can have a directing effect on any second substituent on the benzene ring. And so the important thing to know about this is that it can change the position of substitution. So when the rings go through substitution reactions, where we place the thing that's being substituted depends on the different groups that we already have on the benzene. And so, for example, we can look at the bromination of phenylamine. So phenylamine reacts more readily with bromine compared to benzene. And the amine group directs the second substituent to positions 2 or 4. So what we have is we have phenylamine. And this reacts with some bromine. And then we have benzene again with the amine. And then also we have bromine here and a bromine here and a bromine here. And we also form 3 hydrogen bromides. So we can see that all these bromines have been directed to positions 2 or 4, because if we label this carbon 1, because we're using phenylamine as the kind of root of the name, this would be 2 and then 3 and 4. And if we labeled them anti-clockwise, then this carbon would be number 2. And so we see that the amine group directs the second substituent to positions 2 or 4. And the product we formed is 2, 4, 6 tribromo, because we've got 3 of these bromines, and then phenylamine. And then now the second example is the bromination of nitrobenzene. So what happens is that nitrobenzene reacts more slowly with bromine compared to benzene, and it also needs both a halogen carrier catalyst and a high temperature. And so the nitro group directs the second substituent to position 3. So what we have this time is we have nitrobenzene, and then we react this with bromine. And this time we also only get 1 substitution. And we get benzene with the nitro group on it, and we're now putting the bromine on position 3. So if this is carbon number 1, then we have number 3 here. So we have a bromine. And again we form HBr. And the product we formed is 3-bromo nitrobenzene. And now we're going to look at 2 rules. So the 2 rules are that all 2 and 4 directing groups are what we call activating groups. And this is with the exception of halogens. And all 3 directing groups are deactivating groups. So the definition of an activating group is a group which makes the aromatic ring more susceptible to electrophilic attack. So basically it'll more readily react with electrophiles. Whereas for deactivating groups, they are groups which make the aromatic ring less susceptible to electrophilic attack. And so substitutions will be less likely to happen. So if we go back to our 2 examples, then we can see that the amine group here, amine group is an activating group. Firstly, because it's directed the electrophile, the substitutions, to positions 2 or 4. And also because we get 3, and so the benzene ring must be a lot more susceptible to electrophilic attack because we get 3 substitutions instead of 1. However, when we look at nitrobenzene, so what this tells us is that this nitro group is a deactivating group. because it directs the second substituent to position 3. And also because we only get one substitution and we don't get any more. And so that means that the benzene ring must not be very susceptible to electrophilic attack. Now we're going to look at how to predict substitution products. So using our knowledge of 2, 3, and 4 directing groups and their effects on the position of substitution, we can predict substitution products. And a table like the one below will be given if the question doesn't state whether a group is an activating or deactivating group. So you won't be expected to know. So for example, methylbenzene reacts more readily than benzene with bromine, forming approximately 67% of one monosubstituted product of methylbenzene and 33% of a second monosubstituted product. Draw the structures of both organic products and suggest which product is formed in the greatest percentage. So the first thing it tells us, the question, is that methylbenzene reacts more readily than benzene. And so this means that this methyl group is an activating group. And we know that activating groups direct the second substituent to carbon 2 or carbon 4. So we have that bromine will be directed to carbons 2 and 4. And so what we have is, firstly, let's draw out the methylbenzene. So it looks like this. We have the benzene hexagon, and then we have a methyl group. And so what forms when we react it with the bromine is we get a benzene with the methyl group, and then we have also a bromine on the second carbon. Or there's also 2 other products we could form. We could also form benzene like this, and then CH3. And then if we label the carbons anti-clockwise, this is the second carbon. And in addition to these 2, there's also a third one. Benzene again. And then we have the methyl group. And this time we have the bromine on the 4th carbon. And now what we can see is that here, these 2 are actually the same. So they are equivalent. And that's because if we flip it around, it's exactly the same molecule. And the name of this would be 2-bromobenzene. And for this one, this would be 4-bromobenzene. And also, we know that only one substitution happens because the question says that we form monosubstituted methylbenzenes. And so we can see that there is way more percentage. So the ratio of 2-bromobenzene being formed compared to 4-bromobenzene is a 2-to-1 ratio. So we have the ratio of 2-bromobenzene to 4-bromobenzene is 2-to-1. And so that means that we must have 67% of this 2-bromobenzene and only 33% of this 4-bromobenzene. So now we're going to look at using directing effects in organic synthesis. So the directing effect of substituent groups can be used when planning an organic synthesis. And when carrying out more than one electrophilic substitution reaction on an aromatic compound, we may have to consider the order in which the reactions are carried out to ensure the correct substitution pattern and that the required product is prepared. So the overall method we have is that, first of all, we work out what type of dye substitution it is. So basically what that is we just work out which numbered carbons the substituents are on. And then for step 2, we identify the directing effects of these two substituents and work out which substitution will take place first. The third step will be to write out the 2 steps with the reagents needed for synthesis, and the last step may or may not be used, but it's only used if there's a mixture of products formed, and when that happens, we need to describe how we would separate these products. So I'm going to look over a quick example. It's to suggest a 2-step reaction that could be used to carry out this following synthesis. So for step 1, we have to work out the type of dye substitution. So the product we see is a 1,4 dye substitution product. So we have a 1,4 dye substitution product. Because if we label some of the carbons, we would have to give one of them number 1 because we need the lowest numbers. And so we'd have 1, 2, 3, and 4. And if you labeled it the other way, you'd still have the other substituent on 4. And so what this tells us is that after the first substitution, that substituent, which is on the benzene, will need to direct the second substituent to the 4th carbon. And so we have that the first substituent needs to direct the second to the 4th carbon. And so that's all we do for step 1. And then for step 2, we identify the directing effects of these 2 substituents and then work out which one takes place first. So now we use the table. So for the chlorine, we have that chlorine is a 2 and 4 directing substituent group. And then we have that this nitro group is a 3 directing group. And so now we know that our chlorine must be substituted first because we need the second substituent to be directed to the 4th carbon. And so we get that this chlorine needs to be substituted first. Because otherwise, if we substituted the nitro first, we would have the benzene and then the nitro group. And then because it's 3 directing, then the chlorine would be added here on the 3rd carbon. And that's not the product we want to get. And then for step 3, we write out the 2 steps with the reagents needed for synthesis. So this is when we use our knowledge from the rest of the chapter. So we have step 3. So first we're substituting the chlorine. So this is going to be a chlorination reaction. So it's going to be like the bromination reaction. So we need the halogen carrier catalyst. So we have benzene, and then we add the chlorine, and we also need an aluminium chloride catalyst because it acts as a halogen carrier catalyst, because benzene is very unreactive with electrophiles. And so what we form is we have a chlorine attached, and this is chlorobenzene. And then for the second substitution, we're substituting a nitro group. And so what we need for this is concentrated nitric acid and also concentrated sulfuric acid catalyst. So this is the nitration of benzene that we've looked at. And so what we get is a benzene with the chlorine, and then also a nitro group on the second carbon. However, we can also get another product because chlorine is a 2,4 directing group, and so we can also direct the nitro group to the fourth carbon, and so we get a mixture of these two products. So this is where our step 4 comes in, because we have a mixture instead of just the product that we want. So what we say is that chlorine directs this NO2 group to carbons 2 and 4. So actually naming the molecules that we have above. For the first one, we have 2-nitrochlorobenzene, and then next to it we have 4-nitrochlorobenzene. And then we have benzene to start. And so we have that chlorine directs the nitro group to carbons 2 and 4. And so we get a mixture of products. And the ratio of products we actually get is 2 to 1. Because for this 2-nitrochlorobenzene, we could also have the NO2 on here. And this would be the same exact molecule to the one that we drew before. And so we get double the amount of this 2-nitrochlorobenzene compared to 4-nitrochlorobenzene, because we can only form 4-nitrochlorobenzene in one way. And so we get 67% of this 2-nitrobenzene and only 33% of this NO2. And we can say that to separate the mixture, we could use distillation. If they are liquids, or other methods, for example, recrystallization, if it's a solid. So if they are solids.